Sorry. Sí, eso está mirando.
Sí. Vamos a darle aquí a la derecha. Y hide video panel.
Side.
Otra vez more. Y
Igual puedes esperar un poquito. No, hide. Igual tengo que esperar un poco a ver si desaparece el solo. No, no desaparece, no desaparece.
¿lo podéis mover o
Se puede mover, sí, en pantalla. Vale. Perfecto. Ah, vale, genial. Sí. Ponlo ahí.
Okay. Thank you very much for being here, and sorry for the technical delays. Today we have Rafael Logroño García. He did his PhD here in CEFCA with Carlinhos and Jesus Varela. And then he started working in education.
Yes.
But he defended the PhD recently.
Mm-hmm.
And today he's going to explain about the research he did in CEFCA. So, whenever you want.
Thank you. Thank you very much. So, thank you everybody for coming. It's very good to see a lot of new faces. Well, this is the only old face that I recognize here is Carlos. So this is good because it means, in the first place, that CEFCA is having a new life, which I'm very happy about. And it's also good because it means that this is going to be new for you, because if some people would be here, were here, they will be quite bored because a lot of the slides that I'm going to show, they already knew them. So this is good because it's all new for you. So yeah, as Juan said, I did my PhD here. I worked here for 4 years under the supervision of Carlos and Jesus. I finished now it's going to be 4 years that I finished. And I finished all the work. I had everything done, but then it took a little bit of time to finish the document of the PhD and defend. If anyone is interested, later I can talk about this, but let's focus on the talk. And well, these are the agencies that have funded the project, of course, and we are going to start. So this is a talk. This is mainly the talk that I gave for my PhD defense. So it has the structure of a PhD defense, but I'm going to skip some of the slides. There are some of them that I have already taken them out. Firstly, we will give a brief introduction, and then we will see how do we do this main topic of the thesis, which is the estimation of H-alpha emission line fluxes with J+. Then we will see how we deal with data from the OAJ to characterize nearby galaxies. And then, of course, we will see the sample of galaxies that we are going to use for finally performing our star formation studies, our science cases. So let's start with introduction, which I'm going to be very quick because all of you know about this much more than me. So we are going to talk about galaxies, which, as you know, they are systems of stars, stellar remnants, gas, dark matter, all of them bound together by gravity. And of course, galaxies are very different among each other. There are many differences that we can highlight, but we are interested in morphology. That is maybe the one that strikes us the most, at least in the first place, because it's what you see. See that galaxies have very different morphologies, from irregulars to ellipticals, with the spirals in the middle. Here you have the Hubble-Tanning fork diagram, which is used to classify galaxies according to their morphology. I recommend to remember, especially the different kind of spiral galaxies, because we will use them throughout the text. And when we talk about galaxies, of course, we wonder how they form and how do they evolve, where there are many theories, but according to the bottom-up theories, they grow hierarchically from little seeds to bigger structures by merging, turning gas into stars. And in the end, when they have converted all the gas into stars, they have no gas, they have no star formation. There are observational evidence supporting this scenario as the color magnitude diagrams. Here you have a G minus I color versus the R band magnitude diagram of galaxies with SDSS. And as you can see, we have two populations which are widely known, the blue and the red population, that have different properties. The blue ones are spiral with high star formation, with gas content, and the red ones are generally ellipticals with low star formation and low gas content. And what we observe, what we think is that galaxies start to form like this, and they transit through this zone, which is mainly known as the green valley, until they end up in the red zone. But we have a problem, and it is that the observed rate of mergers is not enough to explain this transition between the blue and the red zone. So there must be another processes causing this transition. And also there are, of course, the reverse transition, some of them that seem to go from the red to the blue cloud. So we have to study in more detail the star formation and its relation with other internal and external factors. And of course, morphology and the gas content of galaxies play an important role, are important factors regarding this. Another observational evidence is very related to the previous one, is the star formation rate main sequence. Here you have the star formation rate stellar mass diagram. Here the star formation, here the stellar mass. And as you can see, when we plot galaxies in this diagram, we see again two populations that are related to the ones in the color magnitude diagram. We have the blue, the blue sequence, which is known as the main sequence, and the rotated sequence, which is known as the red sequence. And according to the theories of galaxy formation and evolution, galaxies go evolving, forming stars and getting higher in stellar mass, and eventually they fall in the retired zone. The star formation rate star formation rate main sequence is also important, not only for this, also to assess how the star formation evolves throughout the story of the universe. And as we were saying, morphology and gas content have a very important role in this. Here you can see this star formation rate main sequence color-coded by morphology. As you can see, there is a correlation between the position of galaxies with respect to the main sequence and their morphology. Here you can see as later types are mainly on the main sequence, while earlier types like S0 and also elliptical galaxies fall off the main sequence. And here you see the same with respect to the H1 gas fraction. So as you can see, we have a higher concentration of H1 in galaxies on the main sequence, and as they fall off the main sequence, their gas content also decreases. The star formation rate main sequence, this is a little unfocused, as I can see. Let's see if I can, it should be, okay. The star formation rate main sequence also holds at local scales, in which we know as the spatially resolved star formation main sequence. How do we compute this? Well, instead of computing the integrated quantities, the integrated star formation rate and the integrated stellar mass, what we compute is the stellar mass surface density and the star formation rate surface density in areas inside the galaxy. So with this, we see that it holds the same relation that we see globally holds at local scales. And it's also important to say that the same trends that we have observed globally with morphology and gas content are also observed in the spatially resolved version of the main sequence. Here you can see the spatially resolved main sequence, and as you can see, late spirals are mainly and early and late spirals are on the main sequence, and as we move through the Hubble sequence, elliptical and S0 galaxies fall off the main sequence, exactly as in the global case. So this gives hints that the local processes play an important role on star formation. And of course, we have to talk very briefly about how stars are formed. You all know about this. And of course, we know that when stars are formed, this is because molecular hydrogen clouds collapse under the effect of gravity. And in the end, with a lot of processes in the middle that we are not going to talk about, nuclear fusion starts. When this fusion starts, there is a lot of radiation coming out from the newborn star, and this radiation ionizes the surrounding media. The later recombination of that media generates emission in very different wavelengths, but among all of them, we are going to look the H-alpha. Why? Because it lies in the optical, in the rest frame wavelength, and it is less affected by dust than other tracers of star formation, that for example, those based on the ultraviolet. And before continuing, we're going to talk a little about astrophysical surveys that, as you all know, they have revolutionized astrophysics with the large sets of data for very different scientific purposes. And of course, we know that the spectroscopic surveys provide a complete spectral information, but they offer it in a limited field of view. With integral field spectroscopic surveys, we have partially overcome this, but they still have some limitations, as we will see now. And then, on the other hand, we have photometric surveys that provide a very wide field of view, but they provide also limited spectral information. But as you all know, we can also overcome this. These are integral field spectroscopic surveys that provide spatial resolved data in thousands of galaxies that we have used in the project. And of course, SDSS as a photometric survey that we have, and spectroscopic fiber spectroscopic survey that we have already also used in the project. And of course, we have to talk about J+. I will be very fast about this. And I'm going to explain this. Why are we interested in J+? You all know this. This is the filter set of J+, and we are, of course, interested in this filter, in the J660. Why? Because we have the broadband filters, the continuum, and with the J660, we can observe the H-alpha until redshift 0.017 or 75 megaparsecs of distance. After that, it starts to go out from the filter. So with this, I'm going to place it again. I'm supposed to be full screen.
No. Presentation mode or something.
Y es pantalla completa, pero...
No. Vuelve aquí.
Okay.
Ahora.
Thank you. You are teaching me how to use my computer. With all this, we wonder, is J+ suitable to perform spatially resolved studies of star formation? Of course it is, because we have the H-alpha emission covered up to this redshift, and Vilella-Rojo in 2015 already provide with methodologies to extract the H-alpha emission from the J+ data, although we need to confirm them. And of course, it's also important to see that we can observe large galaxies in the field of view, and we can also observe large contiguous areas. So we are going to be able to observe a wide space. As you can see here in this figure, which was made a long time ago, this is the typical a tile of J+, and here you can see this 10 arc-minute zoom in, where we have 3 nearby galaxies, and here you have the field of view of different integral field spectroscopic units. This is CALIFA, this is MUSE, and as you can see, for example, this galaxy, this is the CALIFA field of view, and for example, this galaxy already is not observed completely with CALIFA, and this one is completely out of the range. So, but we can observe the 3 of them and the 3 of them together. So we can be faster, and with the science that we want to do, we can be faster, and we can observe the whole extent of galaxies. So with this and with J+ at the current stage, with this now, we can have spatially resolved data for thousands of galaxies in the nearby universe. So with all this in mind, what we established was these 2 objectives. Well, first of all, we want to show that it's possible to carry out spatially resolved studies, because we have said that it's possible, but there are some things that we are going to see. It's not straightforward. And then, of course, once we show this, we want to characterize a sample of galaxies, and then we are going to do some science cases and also compare them with previous data, with previous studies, to validate J+. So we are going to start with the estimation of the H-alpha emission line fluxes. As I already mentioned, these methodologies developed by Vilella-Rojo 15 existed, and with these methodologies, we are supposed to get the H-alpha emission from the J+ data. This was tested with let's say mock J+ data, but now passing SDSS spectra, convolving them with the J+ filter set, but now we are going to try them, or we try them with real J+ data. In order to test this, we are going to perform a comparison between our measurements with J+ and between measurements with spectroscopic data. So we are going to compare J+ data with SDSS and CALIFA. SDSS of data from 138 regions with emission line fluxes by the Portsmouth group, and from CALIFA with 20 star-forming regions selected from Galaxies in common with J+. And then what we used at this stage, we used in the first place, we used a science verification project and the early data release, which was the first data that came out with J+. And after, when the DR1 was available, we also enlarged the study with the DR1. So we are going to do this comparison. For J+, of course, we did measurements. We got the photometry of all those regions in the 12 bands. We got the flux. And once we had the flux of all those regions in common with SDSS and CALIFA, we did an R-band match of our photometry with the convolved spectra of those CALIFA and SDSS regions. Why we did this? To correct possible calibration or mislocation offsets. And after that, when we have all this data already, we applied the methodologies of Vilella-Rojo 15 to our J+ data, which basically consists in a removal of the underlying stellar continuum with stellar population models and dust correction and nitrogen 2 removal with 2 empirical relations based on SDSS data. And with that, we got purely H-alpha emission line fluxes in all the regions. So we were ready to compare. And this is what we did. We compared our measurements with the spectroscopic ones. Here you see the comparison. Here is the ratio between the spectroscopic measurement and the H-alpha by J+ measurement. Here is the one-to-one comparison, which will be perfect. And as you can see, all the points fall really close to the one-to-one. This is the deviation from the one-to-one comparison, and here you have the distribution around the one-to-one comparison. And as you can see, the median ratio of the comparison is 1.02 with this uncertainty. Vilella-Rojo 15 predicted this value, 0.99. So we were very happy with this result because it basically matches the one developed with synthetic data. So, and with this, we validate the method to estimate H-alpha emission line fluxes in the nearby universe. And of course, what we were more happy about is that we were comparing very different sets of data, and the agreement was really good. So this was in the early phases of J+, and the result was very, very, very motivating in this sense, because it meant that we were in the good path to perform star formation rate science with J+. But as I already commented, this was a main issue to validate our H-alpha estimation, but we had also to manage all the data to characterize these nearby galaxies. And this is what consumed most of the time of the thesis. I think that we were 3 out of 4 years doing this. So, but I'm going to be very, very brief. So what is the problem? The problem, well, this is not a problem, of course. Each observing night, J+ produces, as you know, thousands of images, and I think it's not called UPAD any longer, right? Or yes? Okay. This here, people work the data impressively, really, and they provide images and catalogs to the community. They provide a lot of very, very good quality data, as you already know. But unluckily, these data are not suitable for our scientific goals. Why? Because the detection of objects in this main pipeline developed by the UPAD is performed with the R-band, and is not configured for large objects. So this is, but we are interested in performing the detection of objects in images that highlight the star formation areas, and we want to do the detection configured for large extended objects, not for point-like sources. So we need to work from the images. We needed to work from the images from scratch to get individual images for every galaxy of our interest, with the star-forming regions in every band, a catalog of structural parameters, integrated fluxes, H-alpha measurements, and also catalogs of spatially resolved fluxes, including H-alpha. So we had a lot of things to do, and that is what we did. We worked from this is in red, this is like the algorithm that we followed, and in red is like the inputs, in green the processes, and in blue the outcomes. So we started from the coded images and the weight maps with the calibration 0 points, and in the first place what we did was a PSF homogenization and a recomputation of the background noise model, because after the PSF homogenization that we did to the worst of the 12, because we, as you know, we have 12 images, and we homogenized the PSF to the worst of the 12. So we had a common PSF among all the images, and then we recomputed again the noise model of the images, because we knew that the PSF homogenization process could alter that. After getting the homogenized images, we applied the 3-filter method to our images. Which is the 3-filter method? This is a byproduct that was in the Vilella Rojo 15 work. As I already mentioned, in this work, they were trying to get a method to measure the H-alpha emission, and they tried different things. And one of the things they tried was to work directly from images, getting the R and I bands to trace the continuum in a given pixel, and then the J660 to trace the excess. With a very simple equation, we could get the H-alpha plus nitrogen 2 in every pixel, but then in the end it was discarded because the SCD fitting method was much better, because well, this is not the topic of this talk, I can talk about later. But this 3-filter method was very useful, proved to be very useful to produce images with the excess of H-alpha plus nitrogen 2 in every pixel, as you can see here, which is an R-band image of a J+ tile with 2 big galaxies. And here you have, after performing the 3-filter method, as you can see, all the pixels that don't have an excess in the H-alpha plus nitrogen 2 emission disappear, vanish, and then the ones that have this emission are highlighted. So this is a very good thing that we can use to detect the star-forming areas of our galaxies. But of course, to study galaxies, we needed a list of galaxies. So this is also a very important phase of the project, which is to select the sample. So we will talk about this later, but when we have a list of galaxies that we want to study and that we know that are in our J+ data, with the Milky extinction data, we perform a cross-match with the footprint of J+. We get a list of galaxies in the footprint. Then we detect in our images the galaxies in the R band. We get some structural parameters of galaxies. We did this with Sextractor, which in the end turned out to be not the optimal choice, because in order to get structural parameters of galaxies, of large galaxies, well, Sextractor, especially with the half-life radius, as we will comment, we were not very happy about that, but we saw that in the end of the project. And then after doing that, we obtained individual images in all the filters with the PS homogenized, with everything for all the galaxies in our sample. So this is an example of a galaxy. This is the J+ name, but I don't remember the NGC name. It was an NGC. And here you can see in all the filters and in the H-alpha plus nitrogen 2 image, highlighting the star formation areas. After that, from the galaxy images, we perform the detection of star-forming pixels, and with the detection of the star-forming pixels, we say, okay, we consider these pixels as emitting and the other one not. Then we filter all the images of the rest of the bands with this in order to select which areas are star-forming or not. Why do we want to do this? Because if we localize the photometry only in the star forming areas, we will increase the signal to noise ratio, and our measurements will have less uncertainty and everything. So we did this, as I commented, with the H-alpha plus nitrogen 2 images. And what we did was following a simple approach. We said which pixels are emitters, which pixels do we consider as emitters. So we did a distribution of all the pixels in the H-alpha plus nitrogen 2 image, which is, this is an example of the distribution in this galaxy, and basically resembles a Gaussian. And then we computed the standard deviation, and then we consider these different thresholds. So they say, okay, we are going to select what happens if we select all the pixels, which is this. What happens if we select the ones above 1 sigma, which is this. What happens if we consider, and we see, as you can see, as we increase the threshold, the distribution is much more restrictive, until in the end, if we select 5 sigma, all of the pixels vanish. So, okay, we had this method, but then we wondered, okay, which threshold value should we use? Because what happens, maybe we are too restrictive, or maybe we are being too very little restrictive, and we are considering every pixel as emitting. So we did a simple exercise. Once we had the sample of galaxies already selected, we processed the sample and got the H-alpha emission for all the galaxies with different threshold values. And then we did it for -5, -4 sigma, -3 sigma, until 5 sigma. And then we computed the ratio between a given threshold and the one at -5 sigma. Why -5 sigma? Because -5 sigma is like selecting all of them. So we were computing this ratio, which is, here you see the points represent the median with a given threshold, and the lines are the fluxes of every galaxy with the different threshold. And with this, what we saw was the following. As we saw below 0, if we selected a threshold below 0, we were considering non-emitting pixels. And if we selected a threshold 0, we were of course maximizing the H-alpha emission, but we were not considering any uncertainty. So basically everything that was strictly a little bit about 0 was considered as star forming, and this could cause problems, because we will have been surely including non-emitters, for example, as diffuse ionized gas. And with thresholds above 1 sigma, for example, 2, 3, 4, 5, we were seeing that we were being very restrictive, because we were losing, as you can see, a lot of flux. So we thought that threshold 1 is a good balance between catching emission, but also keeping a margin of uncertainty and avoid false emitters. So that is why we selected threshold 1 for our studies. As you can see here, there is a green line that we call Sextractor, because we also performed this study with Sextractor in order to see that our method was similar to the one to the data that Sextractor was giving. Of course, this is for star formation, because we are talking about H-alpha, but for example, to estimate the stellar mass, we were taking images with all the pixels involved, not only those emitting in H-alpha. And after that, after doing this, we were ready to perform aperture photometry and gather all the fluxes and uncertainties for all the bands, not only for integrated galaxies, but in ellipses of increasing size from 0.3 to 3 half-light radius. In this way, we can sample the galaxy in 2D, spatially resolved. As you can see in these images, this is an image of the annulae considered in a galaxy. So we were getting the fluxes and the H-alpha flux in every annulus of this galaxy. In this way, we can trace the radial profile and the radial evolution of the star formation rate along the galaxy. So with this, we were very happy, because we have obtained everything that we wanted to, and we also try to do it in the most automatic way, so it can be applied with minimal interactions to actual, this is not future, this is actual current J+ data releases. But after doing this, we say, okay, let's compare. And what we did was to compare our radial profiles of 12 galaxies of J plus with galaxies that were in common with CALIFA DR2 delta, matching the profiles as you will see at half-life radius 1 to avoid issues due to different calibrations. And as you can see, when we compare the star this is the star formation rate radial profile, we find a very good agreement. In green, you see the measurement by J plus, and in red by CALIFA. And one thing that maybe strikes you the most is that, as you can see, we get to a higher radius, because we, of course, are able to observe the whole extent of galaxies. But what we were more happy about is that we have very similar profiles following the shapes, considering all the differences between the data sets. So we were very happy with this result that, along with the H alpha result, was proving that star formation rate science could be done with J plus. So with this, we already started to do science. Well, first of all, I have to comment very briefly the selection of the sample, which took us a little bit of time because, of course, we needed a sample. We only had the DR1. So we selected a sample, which we called as the J plus DR1 nearby star-forming galaxies. From now on, I will call it the BR21 sample because it's detailed in this paper. This sample had 805 galaxies, which at that time, it was a huge quantity of galaxies for us. We were very happy with the 100 galaxies. I guess that now you think this is too few, but we did a cross match with different databases to assign spectroscopic redshifts, and we found that 647 had a spectroscopic redshift and 158 without. And we also checked for all the galaxies, if we had distances with redshift independent measurements with external databases like NET or SIMBAD. For all the galaxies, we estimated the star formation rate according to the KennyCat 99 calibration with a salpeter IMF, and the stellar masses with this color to mass light ratio estimated by Carlos with Alhambra data. So what about the morphology? We visually classified all the morphology, all the galaxies in the this. No, yes, I have. Creo que lo he pisado o algo así, o no sé qué. I have stepped over the cable and it has disconnected. Okay. So we visually classified the 805 galaxies. This was a very entertained time in which we were looking all the galaxies one and again, because we didn't have time to develop for example, a methodology like today with neural networks and everything, but it was very satisfying to classify galaxies and to observe galaxies and galaxies. And in the end, we end up with these numbers. So as you can see, we have here the galaxies according to the Hubble type, and we have similar numbers, maybe a little bit less for S0s. And we have an overpopulation and overestimation of what we call dwarf compacts and irregulars, which represent 54%. Is where we didn't look into much detail these galaxies. We were not interested in them at that time. We were more interested in the spiral ones, but these were very small galaxies, dwarf compact, but like emitting a lot, very blue in the nearby universe. And yeah, with that, what we did in the first place was to compute the star formation rate stellar mass relation that you can see here. And as you can see, we found, of course, the trend that had already been observed in the literature with galaxies falling on the main sequence. We also computed this relation according to the color coded by the U minus G color. And as you can see, there is also a correlation with this color, and with this, we define the blue sample as galaxies on the main sequence that have these bluer colors in this relation, and the red sample as galaxies that are slightly off the main sequence. We used the blue sample to define the main sequence of a star formation, to define this main sequence that we fit with a log linear fit, and we obtain these best fitting parameters that we, of course, compare with the literature. We compared this work, these values with CALIFA and MANGA data, because they are integral field spectroscopic service, and we are interested on them, accounting for the IMF changes and the redshift evolution. Here you can see the comparisons. The blue line represents the J plus main sequence, and then in the different, for MANGA and CALIFA, in the different colors, you see the different studies. And we found a very good agreement despite the different origin of the data. At this point, we wondered what was the effect of inclination of galaxies in our star formation rate estimations, because we hadn't done any cut regarding inclination. We hadn't selected galaxies above a certain angle of inclination, because we had 805 galaxies, and we said, okay, instead of saying we are going to get rid of 200 or 300 galaxies, we said, okay, well, let's try not to do it, and let's see what happens with these high inclination galaxies. So we, of course, think that inclination can cause a difference between the intrinsic and observed star formation rate, because it's not the same to have a face-on galaxy that is sending us all the radiation and edge-on galaxies in which we cannot see the part that is below the bulge of the galaxy, which is exactly what happens in the Milky Way. So in order to do this study that we wanted to do, we needed to have in mind the morphology, because of course morphology has a main role on how inclination affects, because it's not the same for a very disky galaxy, very thin galaxy, than for a more spherical galaxy. And we did an assumption. We said, okay, the position of galaxies in the star formation rate stellar mass diagram with respect, and their position with respect to the main sequence of the star formation should be the same regarding morphology. It should not be affected by inclination. Should not be affected by inclination regarding the morphology. I mean, all the SC galaxies, all the SD galaxies, all the S0 galaxies should have the same position with respect to the main sequence, regardless of inclination. So what we did was to compute the deviation of the star formation rate from the main sequence for every galaxy that we call delta, and then we adjusted a linear fit of it with respect to inclination for every morphological group, as you can see here. And what we found is that there was, as you can see, the slope that should be zero, and slope zero would mean that we have no evolution of this deviation of the main sequence with respect to inclination, but we found that the slope was not zero, especially in SD, SC, and SD galaxies, and SA. And as we can see, this slope increases steadily with Hubble type. In this plot, you can see the median slope, and from S0 to SD, it increases steadily. And as we can establish that late type galaxies suffer more from inclination effects. SA galaxies break the trend, but are compatible still with 1 sigma. We will talk about this result briefly later. And what we did was to perform a fit of these values to get definitive slope values for every morphological in order to see, okay, this is how SC deviate, this is how SB deviate, and with these values we corrected the effects of inclination. So using these equations, according to this assumption and to this, which is a logical, we got this equation with this we can estimate the deviation for a given galaxy with a certain morphology at a given inclination, and we used the derived values for the slopes for the different morphologies to compensate the observed star formation rates and turn them into supposedly into the intrinsic ones. We did this only, of course, for galaxies that had this slope, different to 0. But in the end, with this correction depends on the inclination. So in the end, this correction basically affects to SC and SD galaxies that have this value around 0.2 dex, and with high inclination. Okay, so most of our galaxies on the sample are not affected by this correction in the end, but we wanted to do this instead of, as I said before, retiring galaxies from the sample. So with all this study, we already had all the data, and we had already performed some science cases, but we wanted to do more. And now we are going to see the star formation rate studies with J+, considering morphology and gas content, as we said in the beginning. And here you can see the star formation rate stellar mass relation, and with the star formation rate main sequence color-coded by morphology. This color coding morphology is the same that I showed before, and it's going to be the same in all the plots. And as you can see, the star formation rate increases with stellar mass from irregulars, peaking at SC galaxies and then falling off the main sequence for S0 galaxies. Maybe you can see it here, which is a 2D histogram in which in each star formation rate, stellar mass being, the main population of galaxies is represented according to this color. And as you can see, we get redder colors as we move along the main sequence, and especially off the main sequence. We did this, we separated the star formation rate in the different morphological groups, and we, of course, when we separate it, we observe this trend between the Hubble type and the position with respect to the main sequence. We see this in the points, but also in the individual main sequence feeds that we computed for each group. As you can see, the main sequence of each of the groups also follows, for this one, for example, is above the general main sequence. This also here, and here in the SV starts to fall off the main sequence. SA galaxies call our attention because, as you can see, they are both on the main sequence and off the main sequence. They have like these two populations, and both on and off the main sequence. And S0 galaxies are completely off the main sequence. Here we have the deviation. The deviation from the main sequence for each morphological group. So here you can see the deviation for the irregulars and the deviation from the S0. And as you can see, this is the distribution of the different deviations for every galaxy. And here you can see the median deviation from the main sequence for every morphological group that is also plotted here. And as you can see, we follow a trend also with Hubble type. And as we can see, SD galaxies are those more above the main sequence, and S0 galaxies are those most off the main sequence. So we are clear that we observe a correlation between the position of galaxies in the main sequence and the morphology. And these results agree with previous study made with integral field spectroscopy, made with SAMI, made with MANGA, and made with CALIFA. We highlight here a comparison of the parameters of our individual feeds, those feeds of the main sequence done for the SDSS, SV, and SA galaxies, with this work by González Delgado 2016 with CALIFA. And as we can see there, the comparison is really good. SVSC feeds are 1 sigma compatible. SD feed is more tight, but is still less than 3 sigma compatible. But SA feeds are really, really different. And so we were starting to gather a lot of things with SA galaxies. So we decided to look closer to our SA galaxies. And as we already commented, they are all both on and off the main sequence. They present a very high dispersion in the star formation rate values that we already saw in the inclination study. So what we found is that in the literature, SA and S0 galaxies present star formation rates up to 2 dex below the lowest values that we observe. As you can see, for example, here, this is a plot by Medlin made with SAMI, and this is our limit. We don't see any galaxy below this line in the star formation rate and stellar mass. And here they observe a lot of galaxies that are S0 and early spirals that we don't observe. So why don't we observe these galaxies? So because we are not able to observe, because our selection that we perform with one sigma threshold other things have filtered out any non-star forming galaxies. So that is why we find this discrepancy, because our SA galaxies, the ones that we observe, and S0 galaxies, even though they are of the main sequence, they are not retired. They don't belong to the retired zone. They are most surely in the what we call as the green valley between the star forming and the passive areas. If they were in the retired zone, we would not observe them because we would never detect them in the 3-filter image that we talked about. So we confirm this, and it's not any problem, but we must take this into account. This whole thing is useful for star-forming galaxies. We are not going to be able to observe with these methodologies retired galaxies because, of course, if there is not any pixel that presents a star formation, so we are not going to detect them. Regarding gas content, because we already commented, we wanted to check this correlation and this relation between the position of galaxies in the main sequence and their gas content. We tried to do this with H1 and H2. We finally could only do it with H1 because we didn't find any data for H2. We only found data for 15 or 16 galaxies, but we found data of H1 for 273 galaxies with these two service nibbles and alpha alpha. And with the data, we computed the H1 flux, and with that H1 flux, the H1 mass. And with that, we computed these two quantities, the H1 gas fraction, which is the ratio of mass in H1, and the ratio and the stellar mass. This is a good indicator of the evolutionary stage of a galaxy because it relates the mass that is still in a gaseous form and the mass that has been converted into stars. And we also computed the star formation efficiency, which gives us the rate at which gas is being converted versus the available gas. So it's a good indicator of the efficiency of the galaxies turning this gas into stars. And here we color-coded our star formation rate stellar mass relation according to the H1 gas fraction, and here according to the star formation efficiency. As you can see, in this case, we observe a correlation. Galaxies on and above the main sequence have higher H1 gas fractions, and galaxies off the main sequence have lower H1 gas fractions. So we find this trend with main sequence, something that we don't find at all with the star formation efficiency. We don't find any correlation of the star formation efficiency and the position of galaxies with respect to the main sequence. Here, we divide the sample in morphologies, but in this case, given that the sample had been reduced to 273 galaxies, we couldn't do it in the Hubble types, but in the irregular, late, and early, simply. And as we can see, there is a significant evolution. This is the distribution of the H1 gas fraction values, and there is a significant evolution with Hubble type. And as we can see, the median H1 gas fractions evolve with the Hubble type, being lowest for early types and highest for late and irregulars. And as I already commented, we didn't observe the same for star formation efficiency. We observed mostly very similar values for the different morphological groups. We compared these results, the ones that I showed before, qualitatively with some studies, and they were in agreement. But regarding the H1 gas fraction, what we did was to compute this. Here we can see the H1 gas fraction versus the stellar mass, and in this plot we can see the comparison with those performed with the service that we have taken the data from, with nibbles and alpha alpha, and they observe the same, a steady decline of the gas fraction as the stellar mass increases. So we found a very good agreement with these results. And regarding the star formation efficiency, we also compared with work that had studied the star formation efficiency. Here you have the star formation efficiency versus the stellar mass, and we found, as we had already seen, that it's relatively constant with morphology, so therefore also with mass. And what we found is that is constant at minus 0.8 logarithmic. And this is the same that had already been found with previous studies, that remains constant more or less around minus 9.5 years. This doesn't happen with H2, this happens with H1 for different reasons that we are not going to comment now. So after that, we of course wanted to go local, and we wanted to study the spatially resolved star formation and sequence, because we had all the data for that. We had the spatially resolved data in the different annuli of the galaxies. So we performed this 2D histogram of the stellar mass surface density and the star formation rate surface density that is plotted here. And as well, this is the 1 sigma 2 sigma 3 sigma contours of the distribution, and as you can see, we observe the same relation that for the global main sequence we find that galaxies, or in this case areas of galaxies, fall along a main sequence, and we perform this log linear fit, and we got these parameters for our fit with these values of the slope and the intercept. And of course, we made a comparison with studies made with integral field spectroscopic data. Well, this is our work, and here you see comparisons with CALIFA, MANGA, and other integral field spectroscopic data. And the first thing that can strike us is that there is a big dispersion, but not of our data with theirs. No, even among their data. I mean, inside CALIFA, inside MANGA, there is a big dispersion with this, and this is understandable because this result is highly dependent, first on the sample of galaxies, and of course, on the methodologies to estimate these quantities, the surface density of star formation rate and stellar mass. We are happy with our result because the one that resembles the most is this one, this pinkish line here, which is the one by Sanchez in 2015, which is the only one that measures the star formation rate, surface density, and the stellar mass surface density in a similar way that we do, which is in regions. They are not regions in our case, they are annuli, but we can consider them as regions, extended regions, and not in individual spaxels as the other integral field spectroscopic data do. The fact that this is done in regions or in integral field spectroscopy in spaxels brings up differences in the distribution that are observable here. And also we perform this, of course, because we had the data, and we perform this study according and color coding by morphology. And as we can see here, there is also the same trend that we observe in the global star formation rate main sequence, also in the spatially resolved one. As you can see here, with the clouds, which represent the star formation rate main sequence, spatially resolved for its morphological groups, and also with the feeds, we observe exactly the same trends. We observe as the clouds move and fall off the main sequence, and we can see as the individual main sequence for each band deviates as we go, as we advance in the Hubble type. We perform the same plot of the deviation for every galaxy, the deviation of the main sequence, and we plot the median one, and we observe the same trend, also that in the global case. And we compared, of course, our results with matched qualitatively with those made with integral field spectroscopic data, like these ones. But still, we noticed that even though we have differences in the star formation rate, even though we have difference in the stellar mass surface densities, the star formation rate densities are not very different. The range in which they move are not very different in the different morphological groups. So we looked a little closer to this because this is logical in the sense that in a given area, when we select an area that is forming stars, it doesn't matter if it's from a SC, RSD, or a S0 galaxy, because in the end it's some pixels that are forming stars. So these areas are going to have similar star formation rates, of course. But we said, okay, if we observe this, at least late types have much less stars in the past and must be now forming at a high rate compared to the past. And early types that have formed much more stars in the past must be now forming now at a lower rate compared to the past. So we say, okay, even though we observe this, we have to observe a high specific star formation rate and a low specific star formation rate for late types and early types. And this is what we did. Given that we have data in 2D, we did it for in the radial profile, and this is exactly with what we observe. The specific star formation rate profiles scale with Hubble type. Here you have the radial profiles of specific star formation rate as we move through out the galaxy from 0 to 3 half-life radius. So we confirm that late type galaxies are forming stars now at a higher rate compared to those early type galaxies that have formed more in the past. This is a result that had also been observed with other data. So wrapping up everything, in global, our results point to the established bottom-up theories of galaxy formation and evolution. Galaxies move along the main sequence, evolving and increasing their mass, converting cold gas into stars, changing the morphology in the process, and mergers, as well as other processes, of course, are responsible for this. And eventually they grow large bulges like SA and S0 galaxies, and their star formations are quenched or are in the process of being quenched with a lower gas content. So with this, we were very happy because we already had accomplished the two objectives that we had for the project, which of course were not the initial ones, as you can imagine, but in the end, we were very happy with these results because it meant that we were in a very good position to perform 2D star formation rate studies with J+. And of course, there is a lot of work, and I'm not going to talk about that can be done now because we haven't talked about AGNs, we haven't talked about, for example, the presence of bars, we haven't talked about environment because we didn't have enough data. But now this study could be enlarged with all those variables, and we could relate these variables with the processes that turn off star formation in galaxies. And with this, I finish, and thank you very much for your attention. And of course, if you have any question, please ask.
Thank you very much, Rafa, for the very nice talk. Questions?
So in the part, thank you, really nice talk. The part where just 2 slides ago, you were showing the radial dependence of the star formation. So were the spiral galaxies selected to be bulgeless? Because these, because in the center we see no change; it's almost flat in all the different types. So is this because usually for spirals we expect the bulge or the center to be more older, to have less.
Yes, to have this depression. Well, here it is observed in the SD galaxies, and it's not observed well in the SC galaxies. There is also a little depression, but in the S0 galaxies it's not as observed. But no, they were not selected to be bulgeless. No. We find this was already highlighted by the tribunal in the defense of the thesis, and yes, but we find a very almost flat, not a big depression as we find only this depression in the SD galaxies. But I compared these results and basically the depression that I recall works made with Sami and CALIFA, the depression that they observed was not also that big. It was below 0.5 dex as the one we find, except for the S0 galaxies that was much bigger and that we don't observe. But in the rest of the spirals, it was not as I mean, it was not as different to ours. Yes, in the case of the S0. Thank you. Yes.
Well, first of all, congratulations for the very, very interesting work and future.
Thank you.
I have a couple of questions. For the dispersion that you see when you do the resolve main sequence compared with the diffuse surface. Maybe I miss it, but two possible effects that can affect this is first, how do you get rid of nitrogen? And second, of course, if I understand correctly, when you select your H alpha threshold, you get rid of possible diffuse emission, right?
Exactly.
But you get rid of the regions. I mean, you select the regions, but you do not subtract the DIG, right?
Well, we no, we don't subtract the diffuse ionized gas, but we don't expect to have any diffused ionized gas because, according to the most recent studies, diffused ionized gas has an equivalent width in H alpha below 15 angstroms, I think, or below 14 angstroms. And with J plus, we are not able to resolve the H alpha emission line below 12 angstroms. So all our emission is above 12 angstroms, and if we consider that even that, which is a bottom line for all the H alpha emission that can be observed, even if we consider that we are making, and this threshold is 1 sigma threshold, we don't expect to have any diffused ionized gas. In fact, if we expect something, is to be losing some pure H alpha emission more than having a contribution from the diffused ionized gas.
Okay, so this at some point tell us that we cannot work on DIG with the J plus.
I wouldn't do it with J plus. With J plus is much better.
Okay. And my second question is regarding the gas fraction. And so have you tried to maybe the lack of difference in the dependence on staff emission efficiency means that perhaps some part of this H1 is not participating in the staff emission, right? So have you tried to put your data on the Smith chemical law?
Yes, we have tried. Well, I tried this 3D, well, the Smith chemical law with H2, H1, but since we lacked H2, it didn't, we couldn't do it because we needed H2 also. But yes, this is indicative, of course, H1, and especially if we take into account that, for example, alpha is the resolution of alpha, I don't remember, but basically it observes the galaxy and everything around. So in the end, the fact that we are observing this with star formation efficiency can mean that in the end we are observing a lot of H1 gas in the galaxy, and this is a reservoir. This is not, a lot of the H1 gas is not taking place in the, well, it's not taking place in the star formation phase. The H2 takes place in the star formation. So in the end, it's what you expect to find a flat correlation with the star formation efficiency, because H2 should be the one that should show a correlation, but not H1, because in the end it's a reservoir. It would be very nice. Now it could be done, this relation of this work with H2, because now for sure we have a lot of galaxies in common with a lot of H2 data. But with the DR1, we only have, like, I don't remember if it was 15 or 16 galaxies, so it was pointless to even do it. But now it would be a very nice thing to do. We even have galaxy. There is a nice study which is called Things. I don't know if you, which looks into the H1 content of galaxies spatially resolved. And there have been follow-up studies also with H2. And I know that, for example, with DR2, we have like 20 or 25 galaxies in common with these studies. And so this could be done with not only in the global case, but also spatially resolved. And also, so yeah, this is a very interesting thing that could be done with J+, definitely.
More questions?
So just to understand the process, so you apply the threshold on the H alpha on the continuum subtracted, right? And then you measure radial profiles on top of those.
Yes.
Right. You didn't isolate label differently the separate
regions.
Start from the regions.
Yes, we did
above the threshold. You just done the radial profile.
We did it also. But
You done
yes,
that?
we tried that in the first place, but
Okay,
it didn't.
but in these results, there's all
No.
radial profile.
This is very
Okay, and then so one thing I tried to understand, I guess I missed it while we were explaining. So for each point in these
This one?
sequence plots, in any of these stellar mass self-formation rate plots, for one galaxy you have 1 point or multiple.
Yes.
So how does that point relate to the radial profiles? Is it the average of the radial profiles?
No, it is this point is the biggest ellipse. Let's say the ellipse that encloses all the galaxy flags, because we have
that's integrated then.
yes,
right?
this is integrated, but then
So
we
is that
have
the result ones?
let me go to this image, which can be very here, this one. So we have data for every little annulus here,
Yes.
like which help us do the radial profile, but we also keep the one inside this one without all of it. So we
Only on the annulus?
only on the biggest one, so we can but not on the whole
Okay,
ellipse,
okay.
taking out all of them, so we have the global one. The background, yes, it's removed from the beginning. Yes.
So sorry, so that's the integrated.
The integrated.
How does the result?
The integrated is only the biggest one, let's say the important.
Yes.
And then we did the measurements in all these annulus,
Yes.
and then we subtracted so we had only in the annulus,
Yeah.
but then we kept the biggest one for the integrated quantity, for the integrated star formation. And so we had the results for integrated and for spatially resolved. When we saw the spatially resolved ones, like in the radial profiles, we see the evolution and what we have. For example, for the main sequence, the spatially resolved main sequence, each of these areas in which we compute the star formation rate surface density and the star mass surface density is each of the annulus. That is. So when we are computing these points, or well, they are not points because they are also in a histogram, each data point in the spatially resolved case is one of these annulus, only considering the pixels that emit star formation, not the whole annulus, but only the pixels inside the annulus that emit in the H alpha percentage. Those are the points in the spatially resolved case.
Okay. Okay, thank you. So I'm just thinking, because mixing all of these different radii for different size galaxies. So you're counting for, except for the radial profiles in the stellar mass self-formation rate plot. The radius is not included, right? So you're just for each annulus you're putting one data point. In. Okay. Thank you.
You're welcome.
Questions?
I have another question. So in principle, you could do that, you could do the similar analysis using, for instance, extracting regions.
Yes.
Okay.
We did it. In fact, we were like 1 year and a half doing it, and in the end, it turned out to be not optimal because it was good for very close galaxies because we could resolve the regions very well, let's say. But when we had for galaxies that were a little farther, it started to fail because in the end we could resolve like 2 regions for a galaxy, and the regions were not real regions, H2 regions, mostly a mixing of regions that couldn't be blended. So we was not optimal. So we decided to follow this approach. But all of the other in the thesis, in the main text of the thesis, I talk a lot about this. But it was developed and it could be applied already to close galaxies because we can resolve regions in close galaxies, and these studies it can be also done with regions in close galaxies.
How do you deal with the extinction correction?
What this was tested already by Belea Rojo 15, and they did it with an empirical relation, taking into account SDSS data, and they performed. There was a color relation, right, Carlos? With the J minus I color, if I recall, Yeah, but we didn't look because I trusted blindly on the on the result.
Basically, when you select star-forming regions, the color is extinguished.
Yes.
But you need to be only in star-forming regions. If you are taking all the color of all the galaxy, then you have all population. Now the color is not that extinguished.
But this result you apply the whole galaxy or each?
Both, yes. In the end, we were all the methodologies that we developed, the ones to extract the H alpha, we did it in every annulus and we did it for the whole galaxy. So it didn't change.
You mentioned something about AGNs. Do you expect contamination in these galaxies?
This is a topic that we left quite unsolved. In fact, if you observe, this is something I was very afraid in the thesis because there are different points here. I don't know if you can observe, but there are points that are present here that are not here. Because this plot was made by Gonzalo, and this was made by me. Why? Because Gonzalo, when he did his work, he retired the AGNs. Because we cannot, of course, we can, of course, establish that we are not affected by diffused ionized gas, but we cannot say the same about AGNs because we cannot perform any kind of diagram, as the GPT diagram with the J plus data, so we don't know.
No, but you have the spatial information. So
Yes.
I would expect that the AGN would move these points up, no? Because it will contaminate the
Yes,
information
yes.
at the given for one of these Green Valley galaxies. But then in the spatial distribution, you would see that it's becoming brighter in the nucleus, but not
Yes.
in the disk.
Yes.
So
In the end, we had 40 AGNs classified by previous data. So given that we were doing a comparison study between the morphologies, we decided to go with them. But of course, if we wanted to look in each galaxy individually, we had to look closer especially into the central zones of those galaxies, of course. But yeah, we decided to go with them because in the end they were also masked with the rest of the morphological groups and it didn't have much impact. We repeated the results with and without AGNs and it didn't have any impact because in the end they were 47 against 800. So
okay, thank you very much. If we don't have any more questions, we thank again the speaker.
thank you.
There will be no seminar next week.
When do you have astropophies now? Or Wednesdays?
Bueno, esto ya lo puede. El Journal Club lo hacemos los jueves.
Ah.
Ahí es donde discutimos papers.
Y el
Voy a parar la.
Vale.